Welcome back, students. We're continuing on talking about radicals now. So we're going to start off with what is known as the principal square root of a, which we write in this notation here, where the symbol that goes down, up, and across, that is called the radical, hence the title of the topic, radicals. Okay, so this is called the square root of a, sometimes called radical a, but really the radical is just the symbol on the outside. So this is the square root of a. So that symbol there is called the radical. The term inside, which in this case is the letter A, we call that the radicand. And the whole thing right there is called a radical expression, or in this case, square root of A. Okay, so now if square root of A equals B, this means that A is equal to B squared. Okay, so for example, if we have that 4 is equal to 2 squared, we would say that the square root of 4 is equal to 2. Now, if we have a different exponent, so if b to the n is equal to a, then b is called an nth root of a, and we can have this for any index. Okay, so on this radical symbol here, we can put an n there, where n could be any whole number greater than or equal to 2, where usually on the basic one, or the principal square root, there's a 2 there that we just don't write. So in here on my 4 I wrote, really this is the square root of 4, where we put that 2 there. But because we use the square root more than any other index, we just don't write the 2 usually. But technically, we can put any number there. And so hypothetically, if we have something that looks like 8 is equal to 2 cubed, we could then say that the cubed root of 8 is equal to 2. Where notice the 3 on the outside matches the 3 on the 2 over there. All right, so now a couple of just quick examples. Down there, we have 100 on the inside of a radical. So this means square root 100. 100 is 10 squared. Sorry about the keyboard. And so we can then say that this is equal to 10 because 10 squared equals 100. Okay. For part B, we have the fifth root of 32. This is going to be equal to 2 because 2 to the power 5 is equal to 32. All right, so we can do this for any number to any power. Generally, though, we only focus on pretty small ones because most people don't have these powers memorized for higher and higher values. All right, so now we have product and quotient rules for radicals, but these are the exact same thing as exponent rules, which is why it's in the same lesson here. So we need to think of the radical rules just like exponents, where if you have the nth root of a times b, that nth root splits up to be the nth root of a times the nth root of b. So just like we distributed exponents, we distribute this radical to both things inside. Okay? And the quotient property is the same thing. If you have the nth root of a divided by b, this is the same thing as the nth root of a divided by the nth root of b, where this radical on the outside just splits up to both things on the inside. All right, so now for number 18, we have the fifth root of 81x squared times the fifth root of 3x cubed, and we want to try to simplify this. So using the product rule right above it, we can put this together to be the fifth root of 81 times 3 is 243, and x squared times x cubed, we saw earlier you add those exponents to get x to the fifth. All right, so now why did we want to do that? Well, this actually simplifies nicely now. 243 is 3 to the power 5. Okay, so again, I'm going to write this little note on the side. 243 equals 3 to the power 5. And so what we can do is pull out a 3 because the fifth root of 243, sorry again about the keyboard, is just equal to 3. And the fifth root of x to the fifth is just equal to x because x to the power 5 is x to the power 5. Hey, go figure, right? And so when we do the fifth root of x to the power 5, we just get 1x left on the outside. All right, for the next one, we have the square root of 320x to the 7th over the square root of 5x to the 5th. We can rewrite this using the quotient rule as the square root of the entire thing, 320x to the 7th over 5x to the 5th. And now, using our rules of quotients from before, we can divide 320 by 5 to get 64. X to the 7th over x to the 5th is x squared. because we subtract the 7 minus the 5. When we move the x to the 5th to the top, it becomes negative and we subtract. And now when we square root this, we're going to have square root of 64 is 8 because 8 squared equals 64. And the square root of x squared is just x. All right, moving on now to rational exponents. The reason this works, what we just did, the reason radicals act just like exponents is because radicals really just are exponents. So when you hear the word rational exponents or the phrase rational exponents, you need to think exponents that are fractions. Okay? When you hear the word rational, you need to think fraction. So rational exponents are fractions that are exponents. So for example, if we have a to the power m divided by n, this is the nth root of a to the power m. Okay? Some people remember this as top dog goes in the house. Okay? Where the top of the exponent goes inside of the radical symbol. Okay, so top dog goes in the house. Whatever's on top of the fraction, that's what goes inside of the radical. And whatever's in the denominator of the fraction, that is the index on the outside. Okay, so for number 19, all we're going to do is rewrite these expressions without the radical. We want to use a rational exponent instead. So if we have the 5th root of x cubed y cubed, we can rewrite this as x cubed y cubed to the power 1 over 5, where it's 1 over 5 because we have this 5th root out here. Okay, that gives us a 5 in the denominator. But rules of exponents tell us that we can multiply this 1/5 in to each of these exponents on the inside. Okay, so this simplifies to be x to the 3 over 5, y to the 3 over 5. And now notice we could have skipped that middle step. Okay, this index on the outside just became the denominator of both fractions on the inside, 3 to the 5th and y to the 5th. Okay, so top dog goes in the house, right? This dog on the inside here, sorry, this top dog on the inside, 3, becomes the top of our fraction. And the index becomes the bottom of our fraction on the exponent. Okay, for number 20, we're going to do the same idea. We have the cubed root of x to the 12th, y to the 14th. This is going to be x to the 12 over 3 times y to the 14 over 3, where we can simplify 12 over 3 to be x to the 4th. And 14 over 3, we can actually just leave as it is, as y to the 14 over 3. If we wanted to, we could simplify 14 over 3 to be a mixed number, but at this point in time, we don't need to. All right, and that is the end of our lesson. Almost forgot. We got to finish off this title slide. Okay, so properties of exponents and radicals. We needed to solve one application down here at the end where we are trying to figure out what ladder is the appropriate size by solving this triangle for its hypotenuse. So remember, we have a 12-foot tall window, 12-foot high window. The ladder needs to be 5 feet from the base of the wall. That created this triangle you see at the bottom of the screen. And we want to use the Pythagorean theorem, a squared plus b squared equals c squared, to figure out what the length of this ladder needs to be in order to appropriately reach the window. So we're trying to find this c right here. So if we set up the Pythagorean theorem, we have 5 squared plus 12 squared equals c squared. This is 25 plus 144 equals c squared. If we add those together, we get 169 is equal to c squared. And so now the reason this is in this lesson is if we square root both sides here, okay, the square root of 169 is 13. So we're going to get that 13 is equal to c, which means that we need a ladder that's at least 13 feet tall. So notice then that the 8-foot ladder is not going to be high enough. Okay, so we need the 16-foot ladder. Okay, we need the 16-foot because if you buy a too short of a ladder, you're not going to safely reach that window. And you could get the 24-foot ladder, but let me tell you, sometimes too much ladder is annoying because you got to carry that thing around and store it. So you don't want to buy a 24-foot ladder if you don't need it. All right, so the reason I bring this up, by the way, is when you have to hang Christmas lights at your house, which at least is something I've had to do in the past, or if you just need to get on your roof in general, this is more or less how you decide how big of a ladder you need. is figure out how far you need the ladder to go and how high you need it to go, and you can find out what length of ladder you're going to need. All right, that was lesson 17. See you guys next time.